Hi everybody. Today we're going to learn about temperature, what is heat, and how to solve what we call heat problems. Okay, first of all, let's kind of get a feeling for temperature. Temperature, I'll just abbreviate it here, is how hot or cold. That's how we commonly think of it, how hot or cold. And we usually do that by comparing to something else, like how hot is that object compared to my hand? So what we're really doing is when we put our hand on a hot object, we're comparing our temperature with the temperature of the hot object. So how hot or cold? A little more advanced definition of temperature is, so I can put that as one. An advanced definition of temperature is that it basically indicates the average motion of the molecules that we're taking the temperature of. So if we're taking the temperature of water, let's say here's the thermometer in the cup of water. What that thermometer is really doing is it's getting an indication of what the average motion is for the various water molecules that are moving around in that cup of water. So average motion. It's really getting an indication of the average kinetic energy. So average kinetic energy. And as you probably learned in the past science classes, kinetic energy is energy of motion. So average kinetic energy or energy of motion. So it gives us an indication of the average. Okay, for anybody in honors, you'll be responsible for a mathematical approach to it. Okay, and so we can do that. We can say, okay, what's the average kinetic energy? The average kinetic energy of a molecule actually equals we have is a constant here, 3/2 first of all, which is constant, times what's called Boltzmann's constant. That's indicated by the letter K. So Boltzmann's constant times the temperature in Kelvin. So that's the temperature in kelvins. Okay. So this is the quantitative way of relating average kinetic energy to temperature in kelvins. We'll get to some examples of that at another time, and I will then include the value for Boltzmann's constant and so forth. But just for now, just to plant the seed, there actually is an equation that relates average kinetic energy of a molecule with temperature. Okay. Now on the other hand, we have a temperature does not mean heat. Even though we kind of, in a practical sense, we think of temperature as being how hot or cold, temperature does not mean heat. What is heat then? Okay, well, heat is a flow or transfer of thermal energy. from a region of high temperature to a region of lower temperature. Okay, so if we want to draw a little cartoon of that, I can draw, let's say, two objects. Let's say two blocks of steel. Sorry, ceiling lights. Okay, so here's one block of steel with a high temperature, and let's place that in contact with the same size block of steel, or similar, but it has a smaller temperature. Okay. Guess which way the heat will flow? Well, which direction will the thermal energy transfer? Okay. You think about that for a second. Okay. Yes, you're right. Okay. The thermal energy will flow from the high temperature region to the lower temperature region. That little arrow there we can think of as the heat that's being transferred. So heat is a flow or transfer of thermal energy from big to small temperature. Okay? So that's one aspect. Now in chemistry, oftentimes heat is symbolized by the letter Q. And the units of heat are, at least in the international system, in terms of joules. Okay? A joule is a unit of heat, just Joule, named after James Joule, and the symbol for it is a capital J. Now, for everyday work, at least in the United States, most of us think of heat or energy in terms of a different unit called a calorie. So the English unit for energy, for a long time, English unit for energy is the calorie. Okay, and it's just abbreviated CAL, period. Okay, and we're familiar with calories because the calories are usually listed on food labels. Okay, but those calories are really kilocalories. So a nutritional calorie, okay, one nutritional calorie, but with a big C, equals is the same thing as a kilocalorie, the little c, and that's equal to 1,000 little calories. Okay, so one big calorie, I should have put cal like that, one big calorie, the big C, equals 1,000 little calories, little c. Okay? Alright, so what does that mean? That means, let's say there's a candy bar, or a piece of candy, and it has, the label on the back says that there are 100 big C calories, or nutritional calories. How many little calories of energy are stored in that candy bar, that piece of candy? Well, that'd be 100 big calories, and each big calorie is 1,000 little calories, so we have to multiply by 1,000. So that's equal to 100,000 little calories. Okay. Now how can we relate that with joules? How can we relate these together? Okay, well, what we can do is realize that there's a conversion factor, and the conversion relating joules to calories goes like this. It's 4.18 joules per 1 little calorie. This is the conversion. .18 joules per 1 calorie. Okay, I'm going to turn the page, and we'll see how that works. Let me get this straightened up here. Okay, let's get back to our 100-calorie candy bar. So here we are again. We have our 100 big-calorie candy bar. And we want to find out how many joules of energy is stored in that candy. Okay, well, as we saw before, we have, I'll just use the factor label method this time. We have 100 calories. And I remember that there are 1,000 little calories per 1 big calorie or nutritional calorie. I set it like that so that the big calories will cross cancel. And then now I can convert little calories to joules by remembering the relationship that there are 4.18 joules for every 1 little calorie. And then we can see that the little calories will cross cancel like that. And that leaves us with what we're looking for, which is the joule. Now if I go ahead using my handy dandy calculator here, see if we can get it so you can see the display. I'm going to take 100, if I can get this to work here, 100 times 1,000 times 4.18. And that gives us 418,000 joules. So the answer to this problem is 418,000 joules. Wow. So you mean to tell me that a 100-calorie candy bar is equivalent to a candy bar that has 418,000 joules of potential energy stored in its chemical bonds? And the answer is that's true. Now, if we want to make it a little bit more fair, I can say, well, let's express this in terms of kilojoules, because a nutritional calorie is like a kilocalorie, so we want to make it fair. So I'll just divide this by 1,000 to convert from joules to kilojoules, and so that gives us 418 kilojoules, which is a little bit more equivalent. The units are a little more equivalent to a nutritional calorie. So 418 kilojoules of potential energy stored in that candy bar. Okay? Next step, let me just put a line here. Let's take a look at the aspect that of what's known as specific heat capacity. Specific heat capacity. Oh, I didn't spell specific right, did I? Specific? Let's try that again. Specific heat capacity. Alright, what the heck is that? Well, we need to know what that means. Let's try to get a little bit of a feel for it first. Let's say that we have different materials that we're going to heat up, and just from your experience, you think about which one would tend to either heat up faster or lose heat faster. Let's check it out. Let's say we have something like water. Let's take 1 gram of water. That'd be like 1 cubic centimeter container filled with water. And let's put a little birthday candle in our little thought experiment underneath that. And we're going to heat that water up. Let's have a thermometer in that water. Let's say the thermometer is so small that it doesn't affect, it doesn't absorb into the heat itself, or it's not going to affect the readings of the water. Let's say we're starting out at 20 degrees Celsius water, and then we add heat to the water. And let's say that 1 gram of water increases by 1 degree to 21 degrees Celsius. Okay, how much heat was given to that water in order to cause the water's temperature to change by 1 degree? So this is a change of 1 degree. T1 was 20 degrees, T2 was 21 degrees. The change in temperature is equal to the final temperature of 21 degrees minus the starting temperature of 20 degrees. So that gives us the change in temperature of 1 degree Celsius. How much heat is needed to do that? Okay. Just maybe you know, maybe you don't. Let's not worry about it at this point. Now let's take 1 gram of something else, like a gram of, let's say, aluminum. So this was water material, and this is going to be 1 gram of aluminum. And let's say that we put a temperature sensor in that aluminum so we can measure its temperature, and we're starting out at 20 degrees Celsius. And this is 1 gram sample. Let's put a birthday candle under there, and we're going to add heat. Okay? How much heat do you think is needed to raise that 1 gram sample of aluminum from 20 degrees to 21 degrees Celsius? Okay? So that we have a temperature change of 1 degree Celsius. So how much heat do you think the amount of heat needed is more than the amount of heat needed to raise the water by 1 degree? Do you think it's the amount of heat is the same as needed to raise the sample of water by 1 degree? Or do you think the amount of heat needed to raise the aluminum by 1 degree is less than the amount needed to raise the same mass of water by 1 degree? Okay, let me write out that question. Do you think that the amount of heat needed to raise 1 gram of aluminum by 1 degree Celsius is more, the same, or less than for 1 gram of water? That's the question I would like you to think about right now. While you're thinking about it, I'm just going to go back and recap. Sorry, that light keeps going off. We have 1 gram of water. We're going to raise it by 1 degree. How much heat is needed to do that? We have 1 gram of aluminum. We're going to raise it by the same 1 degree temperature change. How much heat is needed to do that? Do you think the amount to raise the aluminum is more than that for water? The same? Or less? Well, now that you've thought about it, and we've brainstormed a little bit, we find that the amount of heat needed to raise 1 gram of aluminum by 1 degree is less than that for 1 gram of water. It doesn't take as much heat. All we'd have to do is basically just put our warm hand on that aluminum, and that aluminum would raise in temperature by 1 degree, whereas it would take a bigger source of heat, for a longer period of time, be added to that water in order to raise that 1 gram of water by 1 degree. So water is more sluggish. Water is more sluggish and resistant, has more inertia basically. Water is more sluggish and resistant to added heat. Its temperature does not change as drastically for a given amount of heat added, or for that matter taken away. Okay? So we'll get back to the original term we're trying to explore here, and that is specific heat capacity. Okay? Specific heat capacity also known as specific heat, is symbolized by the letter C. Don't confuse that with calorie or Celsius or whatever. It's just a little letter C, specific heat. And the definition of it is, it's the heat needed to raise 1 gram of whatever, water, whatever, 1 gram of substance by 1 degree Celsius. The heat needed to raise 1 gram of substance by 1 degree Celsius. Need to change pages here. So if we think back to the little 1 gram sample of water, compare that to the 1 gram sample of aluminum, the specific heat for water is a little over 4 times greater than that for aluminum. It happens to be 4.18. It takes 4.18 joules of energy to raise 1 gram of water by 1 degree Celsius. And so we symbolize that. We'll just put CW there for the specific heat of water. That's equal to 4.18 joules per gram degree Celsius. That's how it's usually expressed. This means this. Okay? Let's compare that with aluminum. The specific heat of aluminum is equal to about 0.9 joules. So it takes 0.9 joules to raise 1 gram of aluminum by 1 degree Celsius. And so we'd express that in shorthand by saying C of aluminum is equal to 0.9. It's really 0.89 something, but I'm rounding off. 0.9 joules per gram degree Celsius. So this is a specific heat for water. This is a specific heat for aluminum. Different materials, of course, have their unique specific heat values. Okay. Now let's see what happened there. Monitor. To continue to get a better feeling for what specific heat means, let's think about eating a piece of hot apple pie straight from the oven. And you think about the fact that a lot of times, if you do that, you're going to get burned. Okay? Because of that hot apple pie filling. You don't usually get burned by the crust, though, do you? Why is that? They're both at the same temperature and everything, right? Okay. So, why do we get burned by the hot pie filling, but not by the hot crust? Specific heat, anyone? Let's see how that works. Let's say that the temperature of the hot pie straight out of the oven, the crust and the filling, is 400 degrees Celsius. And the temperature of your tongue is body temperature, and in the metric system that'd be 37 degrees Celsius. Okay, so the temperature change that will be experienced when that hot pie touches your tongue is delta T, right? That's T2 minus T1. That's 400 minus 37 degrees, and that gives us 363 degrees Celsius. Wow, that's a lot of temperature change. So that happens to be an important aspect, or an important factor, when we're considering heat gain or loss. The temperature change, an important factor. Okay? Now, another important factor is the mass of the material. Okay, so first important factor, change in temperature. That's an important factor. Another one is mass. Okay, mass, symbolized by this M. That's an important factor, right? Important factor, because the more massive the pie filling, the more we get burned, huh? So that's an important factor. Mass. Probably don't have as much mass of pie crust compared to the hot filling, huh? Okay. A third important factor would be specific heat, or specific heat capacity, C. Think about the pie filling. It's kind of watery, isn't it, in a way? And remember what the specific heat of water was? It's like 4.18 joules for every gram degree Celsius. So that'd be for the filling, might say. And then how about for the crust? The crust, we could use the analogy of aluminum, right? And this is just for a rough estimate, which was about 1 or 0.9 joules per gram degree Celsius. So look at that. This filling, the filling has about 4 times bigger specific heat than the crust. So, hey, that's an important factor. The specific heat value. Specific heat, important factor. Mass, important factor. Temperature change, important factor. Okay? So, the different factors needed to understand heat transfer would be mass and specific heat, and also temperature change. So we can relate those, and these would be the important factors in determining how much heat gain or loss there is. So we can say that heat is dominated by these 3 factors: mass, specific heat, and temperature change. And there's actually a formula. You remember the symbol for heat, loss or gain, is Q. So we can set Q, heat, equal to, and it turns out that it's just a relationship by multiplying these together. Mass times specific heat times temperature change. And that gives a famous equation. We'll call that mcAT, because if you blur your eyes, that little delta, Greek letter delta, which means change in temperature, kind of looks like a capital A. So here's our mcAT formula. Q equals mc times delta T. M times C times delta T. Very useful equation, and we're going to be using that a lot in here. Let's go on to the next page, and we'll take an example. Let's say that we have 500 grams of water in a bucket, and this bucket is totally insulated, has a lid on it. There's 500 grams of water in there, and I'll put a thermometer in there. And so let's say we're starting this out at 30 degrees Celsius. That's the original temperature of the water. Okay, and over outside here, we've heated up a certain mass of hot. We've got some hot aluminum here. Okay, we've heated up to a temperature of 400 degrees Celsius. Okay, we don't know what the mass of that is. The mass of the aluminum, we don't know, but we do know the starting temperature of the aluminum. That's 400 degrees. We know the starting temperature of the water. That's 30 degrees. Okay, now let's say that we take that hot aluminum and we transfer it, dump it into that bucket of cool water or lukewarm water, and that heat is transferred to the water. And we put a lid on it so we don't lose any heat to the surroundings. And let's see if we can figure out the mass of that aluminum that was in there. Okay, well, what do we know? We know that we have this equation mcAT, Q equals mcAT. But we also know that we can assume, at least just in a simplifying case, that we have the amount of heat gained by the water is approximately equal to the amount of heat lost by the aluminum. So heat gained by the water we can just approximately say that that's equal to the heat lost by the aluminum. Okay? So those are two things we know. This is an expression of the law of conservation of energy right here. Okay? Now if we substitute mcAT in for each one of these, we can say, okay, the mass of the water times the specific heat of the water times the temperature change that the water goes through, that's the heat gained by the water, is equal to the mass of the aluminum times the specific heat of the aluminum times the temperature that the aluminum has gone through. Okay? Now let's go ahead and substitute in what we have. The mass of the water was given as 500 grams. I won't put the units in. The units that we don't want are going to cancel. You can trust me on that. And remember what the specific heat of water was? It was 4.18 joules per gram Celsius. And the temperature of the water, what would that be? Well, if we take 30, we need to know what the final temperature is. Oops. Well, let's say that when you put that hot aluminum in, it goes up by 3 degrees to 33 degrees Celsius. Sorry about that. I should have had that before. So the temperature change of the water then would be 30 from 33, or 3 degrees Celsius. Now, on the other side, we don't know what the mass of the aluminum is, so we're going to have to leave that as just M. But we do know from the previous page what the specific heat of the aluminum is. That's 0.9 joules per gram Celsius. And we can figure out what the change in temperature of the aluminum is, because it started out at 400 and it cooled down to 33. So if we take 400 minus 33, that will give us, let's clear this calculator. I ain't so good at math, guys. We get 367. So the change in temperature is 367 degrees Celsius. Okay. And now we can solve for M. What I'm going to do is make it simpler by cleaning up a lot of this. I'll multiply 500 times 4.18 times 3. And actually I already have it done. If I multiply those together, it comes out to be 6,270 on this side. And then on this side, if I multiply 0.9 times 367, I get 330.3. So this is equal to the mass of the aluminum times 330.3. Now I can divide both sides by 330.3 to solve for M. Okay, and so we get the mass of the aluminum is equal to 6,270 divided by 330.3, and I've already done it on a side sheet, and that gives approximately 18.9 grams of aluminum. So see, we've solved for the mass of the aluminum by using the heat formula called mcAT, and by using the law of conservation of energy, which says in this example that approximately the heat gained by the water is equal to the heat lost by the aluminum. We've used the concept, the three important factors of mass, specific heat, and temperature change, and we've taken advantage of those concepts to get our solution to the problem. Thank you.